I will give you a presentation about my a part of my thesis work entitled "On Exotic Linear Materials, 2D Elasticity and Beyond." In fact, this is under the supervisor of Boris Desmorat and Nicolas Offray at laboratory of Allenberg, Sorbonne University. After the introduction of the architectural material, I will give a brief presentation on the study of the linear elasticity tensor space, and then to stratify this space by symmetry classes. And this notion followed by the conception of exotic materials. In this part, I will give a definition of what is an exotic materials and some interpretation about exotic material in 2D linear elasticity. And this idea will be generalized in all kinds of constitutive laws in 2D and in linear elasticity in 3D. My presentation will be finished by perspective. So first of all, architectural material have been undergone fast growth over the last decades. And compared to the bulk material, architectural material will incorporate the geometry as a new variable which allow us to think about their non-classical effects for a particular designed architecture. So this topic will be studied to the simplest case, linear elasticity, and will be studied in our Max OASIS projects along these three cases. And each case represents one case of non-classical effects, like instabilities and dispersive of wave propagation, as presented by Sad. And what I present today is about anisotropy of linear elasticity. Normally, for anisotropy, there is a correspondence between the properties of anisotropy and its symmetry. Material symmetry. But we call exotic anisotropy is for the material under a stress. It behaves more symmetric than it should be. So the objective of my test is to find all the exotic material that have this exotic anisotropy properties in 2D and in 3D, and to design them by topology optimization. Here gives a brief review of the background in this research topic. First of all, start from the year 80s, Verschachim, Vernello, and Vanussi, they have put up some basic knowledge to study the linear elasticity space about their anisotropy properties. And then in the year of 2000, Vanussi, he discovered a special autotropic material. But at this moment, there is no concept exists to explain this particularity. Then with the development of additive manufacturing and optimization methods, which encourage us to come up with the idea, we come up with the conception of exotic materials, intending to describe all the materials have such particular property of anisotropy. So for my presentation today, I will give answers to these three questions. What is the definition of exotic material, and what is their properties, and what is apart from elasticity behavior, what is how many exotic situations exist for other constitutive laws? So I quickly give you for linear elasticity. We will introduce the elastic tensor to construct a linear relationship between the stress and the strain. And ERLA here is defined as the space of linear elasticity tensor. With the major and minor index symmetry, you can conclude that dimension for ERLA is equal to 6. Later, to study the properties of anisotropy, we are interested in how a material reacts under under a set of orthogonal transformation. And such transformation is described by the orthogonal group called O2. And this transformation is generated by two types. One is rotation, and another one is reflection. And I introduce here two subgroups. ZK describe, in fact, for all the transformation of rotation. And the DK will describe both the rotation and the reflection. So in my following presentation, the orthogonal transformation acts on the Euler space will represent by the star operation here between the small g from O2 and the elastic tensor C from the space Euler. So to know all the, to get knowledge of all the anisotropic type of elements on the space Euler, we will decompose this Euler space by harmonic decomposition. That means that we will decompose this space as several small harmonic spaces. And the advantage of harmonic spaces is that the elements, all the tensors in this space is totally symmetric and traceless. So with this property, we can say that in 2D case, the dimension of harmonic space of order more than 0 is always equal to 2. So in this case, it makes us more easier to conclude the type of anisotropic. I will present it in the next slide. So now the Euler space is decomposed into two harmonic space of order 0 and one harmonic space of order 2 and one harmonic space of order 4. And the isomorphism of O2 equivalent can enable us to that means that the orthogonal transformation on the elastic tensor can be considered as the transformation acts respectively these four harmonic components, that alpha beta is from the space K0 and small h from the space K2, big H from space K4. So I give here an example of explicit decomposition, which relates these four harmonic components to the elastic tensor. And it is followed by an interpretation of this constitutive law in two parts. One part is deviatoric elasticity, and another part is spherical elasticity. And the elastic tensor C is represented here by these four harmonic components. So I repeat, the idea of this part of harmonic decomposition is it allows us to decompose a large space, a set of small ones. And for each small one, the particularity of harmonic space can tell us their properties of anisotropy. And this is explained by the geometrical interpretation here. It is based on the harmonic. I propose here another notion called harmonic bouquet. It is based on the harmonic bouquet, and this notion is based on the fact that for 2D, the harmonic space of order larger than 0 is always equal to 2. So we can regard, in fact, all these two harmonic components as vectors. So the transformation of rotation theta acts on a elastic tensor of order 2 can be regarded as a vector rotated by 2 theta. And it is the same case that if it acts on the tensor of order 4, can be regarded of a vector rotated by 4 theta. So in this case, their anisotropy type is very obvious. Like for small h, it is orthotropic. And for big H from space K4 is tetragonal. And for alpha beta from K0 is isotropic. And such results, okay, what we talked about previously is about elastic tensor. Now we will move from elastic tensor to elastic materials. It is realized by another notion called orbit. We come back to this model that rotation of a material will not change the nature of this material, but we'll associate it with another tensor. And we consider these two tensors equivalent. And we collect all the equivalent tensors of this material and describe by orbit a circle here. So in this case, we can see the orbit is used to define elastic material. We come back here to the elasticity tensor space. It is possible to be interpreted by another version of orbits. So now to stratify this space or this space by its kind of anisotropy, it is realized first of all by some mathematical notion. I will propose some mathematical notion here. First of all is symmetry group. Symmetry group is defined as the set of transformation that the tensors transformed remains the same as the tensor initial tensor. Sorry, and the symmetry class is defined as the set of subgroup conjugate to a symmetry group, and it is denoted by this. And the transformation, and the stratification of this space by according to its symmetry classes leads us to another notion called strat. So strat is like the set of tensors have the same symmetry classes. And I remark here that for the symmetry class for the tensors in an orbit is always the same. So the stratification of this space by its symmetry classes can allow us also to stratify the space of elastic materials by its anisotropy type. Here is an application for the Euler space to get all the strata of Euler, and it is realized by the eclipse operation. I use here again the harmonic structure. So the symmetry classes of Euler is obtained by the eclipse operation between the symmetry class of K2 and the symmetry class of K4. And for the K2 space, the symmetry class is isotopic and orthotopic. And for K4, the symmetry classes are isotopic and tetragonal. So I give out direct here the result of eclipse operation. I take an example of the eclipse operation between the orthotopic and the tetragonal. It results in the biclinic and the orthotopic. So from this result, we can conclude that the Euler is divided into 4 types of stars. And I illustrate it in this picture with different color for different stars. The gray color is for the biclinic tensor, orange one is for orthotopic tensor, and the blue one is for tetragonal tensor, and the red one is for isotopic tensor. And I remark here that this stratification in this form is based on the fact that the strat is not a vector space. This means that two tensors in a linear combination of 2 tensors in one strat will not necessarily result in the same strat. The result we obtained before will be interpreted here by harmonic bouquet. It depends on 2 mechanisms of manipulation on the harmonic components. First mechanism is the cancellation of at least 1 harmonic component. And then the second one is alignment of 2 harmonic components. And with these 2 mechanisms, you can get for Euler 5 possibilities of the harmonic bouquet. And these 5 possibilities nicely matched the result we obtained before by eclipse operation. For the gray one, biclinic, there is no cancellation and no alignment. So these 2 vectors will rotate independently, and it results in the biclinic. And the second one, orthotopic, these 2 vectors will get aligned. So they will rotate together, and this results in the orthotopic. And the third one is more simple. The cancellation of the big H will remain as just a small h, so it is orthotopic. And the cancellation of small h remains just a big H, so it's tetragonal. and the cancellation of both small h and big H remains just alpha and beta, so it is isotropic. And each case here corresponds to the result we obtained by Eclipse operation. So apart from this, one question arises. There are two mechanisms to get the one same result of orthotopic, either by alignment of small h, big H, or by a cancellation of the big H. So what is the consequence of this diversity? In fact, I put in the parentheses is the minimum number of independent components of elastic tensor. We can see regarding to the four cases at the left side, with incrementally in augmentation of the symmetry degree, the minimum number will decrease also incrementally one by one. So in this case, we can say that these four cases belongs to symmetry classes, but it is not the case for the orthotopic at the right side. In fact, the condition of big H equal to 0 is not a condition of symmetry requirement, but it comes from the design of mesostructure. And the material corresponds to this property called R0 orthotopic material. And this is one example of exotic material. So how we define exotic material? There are two criteria to satisfy. First of all, as I just said, it satisfies the independent constraint of those that may be imposed by symmetry arguments. Second one is that under a given stress, it behaves more symmetric than that imposed by the material symmetry. The second one is a little abstract to understand. I give you 3 photos of sculpture taken apart from different point of view. And in this case, we can see that, in fact, specific choice of the point of view, the sculpture captured in 2D shows more symmetric than itself in 3D. And it is the same case for R0 orthotopic material. The cancellation of the big H gives us globally a material orthotopic. But if we focus on the deviatoric part of this constitutive law, it is isotopic. So it is more symmetric that it not should be. Here I give a quick result about the design of the R0 orthotopic material. It is based on the topology optimization algorithm proposed by Armstrong. It's based on the level set topological derivative optimization. And I give here the level set function to define, in fact, the ellipse inclusion in the unit cell. And then there is some material parameter. This is for the metric phase, rigid metric phase, and ellipse is the soft phase. The initialization like this is, in fact, we want to initiate our algorithm by a normal orthotopic material, as is showed by the effective tensor showed here. And here we got the optimized design. We can conclude that the effective tensor obtained is also, first of all, it is orthotopic. It's in orthotopic form, and besides, we have this condition added, that the vanish of the big H, and it is from the design of this mesostructure. Okay. Now I will apply this idea of exotic material to other constitutive laws. First of all, I give here the formula to calculate all the number of exotic sets for all constitutive laws in 2D. And it is established from the harmonic decomposition. N is the number of harmonic space of order larger than 0, and the small h is the number of harmonic space of order minus 1. And the big S calculates, in fact, the O type of anisotropy. And the C is calculates this type of the number of symmetry classes, and it is calculated from Cliff's operation. And for big S, there are two parts. One part, the blue part calculates the possibility of cancellation, and the green part calculates for each cancellation case the possibility of alignments. So with this formula, I give you an example to calculate the number of exotic sets for piezoelectricity. Okay, for piezoelectricity, besides the relation between stress and strain, we will take into account also the polarization caused by the electric field. So in this case, the tensor of piezoelectric tensor, the space of piezoelectric tensor is composed by three subspaces. Ola is used to define space, to define the elasticity behavior, and the cone is to define the dielectric behavior, and the PS is the coupling of these two behavior previously. So I give you the result here in the table. For Ola, there is just one exotic set, and this will correspond to the R0 autotopic material. And for PS 11 case, and the phone is there's no exotic material. In consequence, for piezoelectricity, there is relatively exploded number of exotic sets, have 530. Later, we apply this idea to 3D linear elasticity. As the 2D elasticity, we define OLA3 as the space for the tensor in 3D, and it is decomposed in two harmonic space of order 0, two harmonic space of order 2, and one harmonic space of order 4. And with operation of Cliffs, we can conclude that there are 8 symmetry classes for this space. And just as what we do for 2D, we want to try the detail of each result. In this case, we can find out, in fact, the exotic sets. But however, it is very complicated for 3D. I give here the result of Cliff's operation in different color, and it is obtained by the combination of 3 symmetry classes, two from the space H2, one from the space H4. And for each result, there is 1 symmetry classes, and all the rest, they are the exotic sets, regarding to the minimum number of independent components here. I will not show all the results here, but we can conclude that there is totally 163 exotic sets for OLA3. So it's relatively exploded in respect to the OLA2. Okay, a small conclusion. We have defined what is exotic materials, and it is realized from the 2D linear elasticity. And this idea is extended to all types of constitutive law for 2D and elastic behavior in 3D. The perspective. First of all, we have to define the condition expressed by covariance for the different exotic sets we have found in 3D case, and then to design the microstructural geometry for 2D and 3D exotic linear elastic materials. We have just give you the example of R0 autotopic. It is realized at MATLAB, and we will reproduce it in Phoenix. And then this machine is innovated by our team, MaxOS's team. It's used to test the mechanical properties of architectural material. So the obtained architectural material, we will test their properties in this machine. That's all. Thank you.